All right. Okay. So where did we end up? Let me just copy the main statement that we had. It's this guy. Okay, let's take two things. So for any graph, we had this theorem that if you had take any signed adjacency matrix, your adjacency matrices are fixed, but now you get to pick the signs. So you have a lot of choices for the signs. For every edge, you can pick any plus or minus one, and you want to pick those signs so as to maximize kind of the largest eigenvalue of the matrix, and that will give us this bound. Okay. And if you had to do this for a single graph, really, the best thing is to just take the adjacency matrix. Putting minus ones, you only can decrease the largest eigenvalue. Okay. But that's not exactly what we are shooting for. So what is the other constraint? If I just tell you, okay, here's a graph, this is its adjacency matrix. Now pick any signed adjacency matrix to maximize this. The answer is basically going to be take the adjacency matrix. Okay. But the catch for us is something else, right? We don't have a single graph that we want to do this for. We want to do this for all subgraphs of a fixed graph. Okay. So in particular, so we have the hypercube graph. Hn, right? So the vertices are bit strings. And the edges, where basically two strings are connected if they differ in exactly one coordinate. Okay. Now, so what do we need to show for this? We need to show that S is a subset of 0, 1 to the n. Size of S is at least 2 to the n minus 1 plus 1. Then right, this is what maybe let me straight it this way so that it's kind of clearer. You can take your hypercube graph, but restrict it to only the vertices in S. So delete all other vertices in some sense. You're ignoring the rest of the vertices. So any edge which is not contained in S also gets deleted. And we want to still say that the largest degree is high. Okay. So that means concretely, and if you want to use the signing approach, we want a signed adjacency matrix Bn of Hn. Okay. So you want some, or at least it suffices to have a signing of the adjacency matrix of the hypercube such that any principal submatrix. I'll tell you what this means in a second. Okay, so what is this saying? Yeah, so this is, let's say, you pick some signing of your hypercube Hn. Now I want to pick this signing such that if I take any set of rows which are from set S, which is greater than or equal to 2 to the n minus 1 plus 1, and the same set of columns Okay. Then the submatrix formed by these rows and columns. So this blue matrix is basically our BSS. Okay, so you have the big matrix. I'm restricting it to some subset of rows, some set of columns. Ignore everything else. So delete everything which is yellow. Only keep the blue region. Okay, so you want to say that if the largest eigenvalue in absolute value of these matrices is at least root n, then we're in good shape. Okay, because when I restrict to S comma S, what I see is exactly the adjacency matrix of Hn restricted to those vertices. I'm deleting everything else. Okay, does that make sense? Okay, so we're going from looking at subgraphs to looking at submatrices. And we say principal submatrix because you had to pick the same set of rows and columns. Okay, any questions about this? Yeah.
Theoretic statement.
Uh-huh.
There's like a way to see why square. I mean, I know it's equivalent to sensitive, but why square root of n will show up? Is there like an example?
There is an example. I'll show you. I'll talk about the example once we do the proof. Okay, it's not a simple example, but you can get an example.
This was before.
Kind of known. It was known in the sensitivity version that the best you could get was square root n, so you could translate that into the graph version. Good question. But so this is what we're shooting for. When in some sense, you didn't even have to do this. Like for every set S, you could have asked for a specific signing, but we're kind of being too hopeful and saying, I'll find a single signing for the hypercube, which somehow works for all subgraphs and all submatrices. Okay. Which is a remarkable thing to hope for. That's a very optimistic view. And I think there's somehow already a big leap. The think that something like this exists is, it's not something I would have suspected before. Okay, that there is a single signing which should work for all things. Okay. All right. But going for such a strong sort of signing gives you a lot of leverage. In particular, if it's a single matrix, I can compute its eigenvalues and so on, eigenvalues, eigenvectors, right? Usually, when you go from a matrix to submatrices, you will lose information about the eigenvalues. Okay, so let's take a simpler version of this problem, right? So in some sense, the question that we are asking, forgetting the graph theoretic origins, is, I have some matrix. For us, this is a signed adjacency matrix, but let's ignore that for now. I just have some matrix. I just thinking of it as the linear algebra problem. Okay, and if let's say I basically remove all but, let me just draw a simple picture. Okay, I'm looking at a submatrix where I remove all but the first row and the first column. Okay, it's again a principal submatrix in the sense that I'm taking the same set of rows and columns. Okay, so I removed one row and column. So these are gone. Okay. Now, if I know the eigenvalues of M, you don't know the exact values of the eigenvalues of the new matrix. And let me call it M minus 1 for simplicity. Okay. So I remove the first row and first column. That's why it's M minus 1. Now, usually we don't know the exact formulas, but there's this beautiful, very old theorem, very old in sense it's not exactly known in this language, but it has rich history around it and phenomenally useful in linear algebra. It's called the Cauchy interlacing theorem. All right. You know what interlacing means? Right. So like, if you think of a braid, it's basically like you're braiding them by interlacing things, right? And Cauchy interlacing theorem basically says that the eigenvalues of M and M minus 1 interlace. Okay, that's the English version. Kind of a very surprising thing that there's so much regularity in these eigenvalues, but that's exactly true. That there is this magical pattern that arises. Okay, so let me first state it in English. So eigenvalues of M. So M is a symmetric matrix, is a real symmetric matrix, and M minus 1 interlace. Okay, so what does this mean? Just imagine I draw a number line, okay, and I plot down the eigenvalues of M. And just for pictorial reasons, suppose they're all different. They could, maybe one is an eigenvalue 2 times, 3 times, that's okay. Let's just, for artistic reasons, let's say they are all separate. Okay. And the gaps between them really can be arbitrary. Given any matrix M, any set of these values, you can more or less build a matrix which has those eigenvalues. So like really you should not expect any pattern here. Okay. Make sense so far? Now, how many eigenvalues does M have? Let's say it's an n by n matrix. It does n eigenvalues. And so I would have n dots here. How many eigenvalues would M minus 1 have? N minus 1. Now, given that I tell you eigenvalues of M and M minus 1 interlace, what do you think it means? The eigenvalues of M minus 1 are basically going to be in these gaps. Okay, so that's the miracle, that we don't know exactly, in every one of them should be between the gaps. They could be very close, very far, maybe right in the middle, who knows, but they should be in between. Just in the, okay, it's not going to go over below. So they're exactly n minus 1 intervals, right? If you put n points, they're n minus 1 gaps, and the eigenvalues of n minus 1 should hit every one of those gaps if they're distinct. If something is a multiple eigenvalue, then that basically means that that red dot should lie on the blue dot. Right? It's like basically these two are getting shrunk, so this one should still be in the gap. So that means it exactly is one of the dots. Okay. So the way to write it formally is, remember we had this ordering of eigenvalues. Right? So if I write down the eigenvalues of M in this order, okay. Now every eigenvalue of M minus 1 should come in between. So that's what we would have. Okay, this is called the interlacing theorem. All right. So even though you don't know the exact values, you kind of have some control on the individual eigenvalues when you take out one row. And any questions about the statement? Okay, so this is when I took out one row or column. Now, what happens if I take out, let's say, 2 rows or columns? Let's say now, maybe this was M minus 1, and I take out one more row and column. And I'll call this, let's say, M minus 1, 2. Meaning I took out both the first row, second row, and the first row and second column. Okay. So what can we say about the eigenvalues of M minus 1, 2? How can I infer some properties of this versus the eigenvalues of M? Any suggestions, guesses? Yeah. Exactly, right? So I don't know how they would relate directly to M, but at least Cauchy's interlacing theorem says that they should be somewhere in between these red dots. Okay. But we do lose some information. So it should be somewhere in between here. But we don't know which side of this blue dot it's going to. Okay. Right. So if I write it down mathematically, somehow, all I know is that I hope you understand this weird notation, but this is trying to show a reasonably complicated pattern. Okay. So we can't compare lambda n minus 2 of m minus 1, 2 and this one directly. Okay. But we can compare it to that or this. Okay. So you can keep going like this. If I remove 3 columns and 3 rows, which is again principles of matrix, then I would interlace here. Okay. And eventually you get a reasonably good relation. And the general relation is as follows. You can just prove this by induction. It's not complicated given the original interlacing theorem. So for instance, if I had to compare those of M1, 2, and M, I know that N minus 2 is at least M. N minus 2 is at least N, and N minus 2 is at most N minus 2. N minus 3 is at least N minus 1 because I go like this. Okay, and you can change some of these inequalities and you get the following. So M is a symmetric N by N matrix. B is a M by M principal submatrix. Okay. Then, and let's say I order all the eigenvalues of M first. Okay, let me use begin here. Okay. And we call this A. A also has the same ordering of the eigenvalues of B. And you can see from here that the n minus 2th eigenvalue was always at most the n minus 2th eigenvalue of the original matrix. The n minus 3th would be at most n minus 3th, and so on. Okay, so that relation holds. So for every I, lambda I of B is less than or equal to lambda I of A. That is true. When you compare for a lower bound, you have to kind of skip whatever things that you did. So n minus 2, you can compare with n. Okay. So in the same way, you would get this. Okay. You can, it's not that difficult to check, like, just do it by induction or something. So for example, m equals n minus 2, we get lambda I plus 2 is less than. Okay, which is what we were seeing here, right? N minus 2 versus n minus 2 plus 2. N minus 3 versus n minus 3 plus 2, which was n minus 1. So you skip 2 down instead of 1 down. Okay. So how many ever things that you took out, that's how many you have. All right. Any questions about this statement? So the proof of this is from by induction of the original statement. But, the original statement, there are many, many, many proofs of that. It's very well understood. Any questions? Okay. So this is going to be our magic bullet, our hammer, whatever you want to call it, and we're going to use that, right? So let's now go back to our problem. So we have this, we're going to try and find some sign adjacency matrix Bn, and then we have to argue about submatrices, which are somewhat big. Okay. So at the very least, once you're talking about principal submatrices and you want to look at eigenvalues, it makes sense to look at what Cauchy's interlacing theorem would tell us. Okay. So if we go back all the way to what we are trying to do, then we have Bn, which is a signed adjacency matrix of Hn. Okay. So this is a, let's say, capital N by capital N matrix, where capital N is 2 to the little n. Right. So the number of rows and columns is 2 to the n. For every bit string of length n, you had a row or column. Okay. And we were looking at BSS. Let me call it, maybe we just call it C, the matrix. Let me just keep it like this actually. For some S of size okay. We are picking at least half the vertices. In particular, let's say we're picking exactly half. Okay. It's strictly one more than the half. And this is, we are looking at the corresponding principal submatrix. Okay. So what does Cauchy's interlacing theorem tell us? By Cauchy's interlacing theorem, we do know that and we are in some sense only interested in the largest eigenvalue of BSS. Okay, we don't care about all the eigenvalues because we just want to say that no matter which submatrix you take, the largest eigenvalue is still somewhat big. Okay. I mean, Cauchy's interlacing theorem tells you a lot more, but I just need one. So let's focus on that. So this is true because it's just a submatrix. And the other thing is it's going to be lambda n minus m plus 1 of B. Okay. So the largest eigenvalue here is always, of course, the largest eigenvalue. But from the graph theoretic statement that we're trying to show, we really care about the lower bound. Okay. And the lower bound is also part of the interlacing theorem. Okay. So we have some lower bound on eigenvalues. In particular, so this is exactly. So in other words, okay, if you substitute in the values, what you get is n minus m. So it's like 2 to the n minus 1, minus 1, but then you're also adding plus 1. So you just get this. Okay. So, it's a very remarkable simplification. I just need to show or find something, some adjacency matrix to satisfy something, and I can argue about all of the submatrices. Okay. So how can I reformulate my goal now? Any suggestions? So our goal was to find a signing such that we could prove the lower bound on the max degree. Now the goal can be rephrased or simplified a little bit. Want a signed adjacency matrix. Such that what happens? So it's a 2 to the n by 2 to the n matrix. It has a lot of eigenvalues, 2 to the n eigenvalues. But what else do we need? Basically, we need a signing such that we don't just maximize the largest one, but I want the kind of 2 to the n minus 1th eigenvalue also to be big, right? Such that if I can show this, I'm very happy. Can you find me a signing which has 2 to the n minus 1 eigenvalues, all of which are at least? Okay. If I can find such a signed adjacency matrix, then this would imply the graph theoretic version by our connection between signed adjacency matrix and the max degree. Okay, any questions about this? Right? Okay. Let's do some, maybe a couple of, one very near example is, okay, let me look at what happens if I just take no signing, but just the adjacency matrix. Okay, just the adjacency matrix. Okay, the actual adjacency matrix, nothing too fancy. Then, each row and column. So these are bit strings. So how many, what's the largest eigenvalue of this matrix, for example? N, right? Because each vertex has degree n, it's a regular graph. So largest is going to be just n. Okay, this is the adjacency matrix. Okay, but it turns out that it doesn't, we were shooting for root n, but we're getting n. But the problem is that it has many, many eigenvalues, which are bad. Okay, much, much smaller. Okay, the largest is much larger than what we want. But if I ask for kind of the middle eigenvalue, that is going to be very small. Okay, and you can check that by a simple calculation. Okay. The eigenvalues of the hypercube are completely well understood. They're basically like n, n-1, n-2, and so on. Okay. And the number of each is like n choose k. When you go to the middle level, you're basically in very small territory. All right. Okay, so that's going to be an issue. So this is not going to work. So we have to find some other actual signing to get that. Okay. And so already we had several sort of clever things. And the final thing that maybe this is also very cool is the following. We'll prove by simple inductive construction that for every n, there exists a signing of Bn such that the square of this is exactly n times the identity. Okay. So there exists a signing such that the square is actually the identity matrix. So what does this mean? So for example, take the 4x4 matrix, right? So let's say n equals 2, then have 0, 0, 0, 1, 1, 0, 1, 1, 0, and 1, 0, 1, 1. And what are the edges? Just 0, 1, 1, 0. Okay, this is the adjacency matrix of Hn, of H2. And the claim is that there is a way to sign this thing so that when I square it, I actually get the identity matrix with some multiple. Okay. So there is a signing so that we get square. Okay. And the proof of this is like, not too bad. I'm just going to write the answer for now and we'll figure out the actual thing later. You can check this, that the square of this, maybe let me just write it down. So this I'm going to call B2. B2 square is actually 2 times I4. Maybe let's do a simple cross check. Okay. So when I multiply it, what do I get? I should get another 4x4 matrix, right? Okay, let's do a couple of computations. This times this is exactly 2. The -1 and 1's match up. So I get 2. And how about this times this? They have no overlap really, right? So the -1's are in the middle 2 entries, they're on the outside. So you get 0. And how about this times this? Again, there's no overlap. So I get 0. This times this, there is overlap, but there's -1, 1 here, and there's 1, 1 there. So I got 0 again. Okay. And if you actually check it, you do get this. Okay. All right. So, we will prove this in a second, but let's see why is it useful for us. If I tell you that the square of this matrix Bn is n times identity, what can you tell me about the eigenvalues of Bn? They have to be square root n in nature, right? So remember, when we square a matrix, what happens to the eigenvalues? The eigenvalues get squared, right? So if a Bn squared equals n times ident2, this happens. This implies that all of the eigenvalues are either root n or minus root n. Okay? Because when I square a matrix, the eigenvalues get squared. The eigenvalues of n times identity are just n, right? So that means lambda squared is n. So lambda should be root n or minus. We don't know how many of root n or how many of minus root n there can. So far, at least. But if our goal was to say that the middle one is at least root n, we need to control that. What if everything is minus root n except the largest? It's not a useful matrix for us. But can that happen? Trace is 0. Okay. Again, there's this another nice property of eigenvalues, which is that for any matrix A, if I add up all of the eigenvalues, it's a symmetric matrix. This is equal to the trace of the matrix are basically sum of the diagonal entries. Okay, so adding up all the eigenvalues is just the same, should give you the same answer as adding up the diagonal entries. Okay. So what does this mean? Well, the trace of Bn, which is just sum of, by definition, it's defined as the sum of diagonal entries of Bn equals, what is it? It's going to be 0, right? Because the hypercube has no self loops. So every diagonal entry is actually 0. So when you add them all up, you should get 0. Okay. Okay. So now we have 2 bits of information or 2 facts about the eigenvalues of Bn. They're all either square root n or minus square root n. And sum of all of them is 0. So what should happen? How many plus root n's and how many minus root n's should I have? Exactly the same number, or in particular, exactly half and half, right? So that means I have a matrix which has 2 to the n eigenvalues, right? And I should have equal number of root n's and equal number of minus root n's. So this implies that Bn has 2 to the n minus 1 eigenvalues that are root n 2 to the n minus 1 eigenvalues that are minus root. Okay, so in particular, you would satisfy this, right? The middle eigenvalue is exactly root. Everything above that is root n, everything below that is minus root n, right? So it's so delicate. Okay, so if you look at the eigenvalues of Bn, there are 2 to the n minus 1, which are minus root n, and then 2 to the n minus 1, which are exactly root n as we want. Okay. All right. So to summarize, if we show that there exists a matrix Bn such that a signed adjacency matrix Bn such that Bn squared is n times identity, we are done. Right? So it's so delicate, you know, exactly half are there, and that's exactly what we need. Right? Okay. That's why, you know, it's kind of a, I said, it's a simple proof in terms when you look at the final thing, but it's miraculous because you wouldn't expect such a delicate balance to actually hold to even pursue it. Okay, any questions about this? All right. So now, you know, given everything that we've done, this actually turns out, I think, is the easiest part. Okay. So how do we do this? Well, let's just do it by kind of examples, right? We'll try and do it for n equals 1, n equals 2. By the time we get to n equals 3, you will identify patterns. Okay. So let's just try it out. So n equals 1. So h1 is just this graph. Okay. Just a single edge. So I'll write down the adjacency matrix and the signing. So what would be a signing which gives me what I want? So what do we need? When we multiply it, we should get back the identity, or 2 times the identity. Any guesses? So if I just do this, I mean, actually, you know, even this matrix works, but let me just write one specific choice, which is better. I'm going to put minus ones here. The question. No, it's basically if you put everything together, we are done in terms of proving even the graph theoretic version, right? Because that would say that the 2 to the n minus 1 eigenvalue is at least root n, which by Cauchy's interlacing theorem would tell you lambda 1 of any submatrix is at least root n, which by a connection to signed adjacency matrix would tell you about the degree. Okay, it's a sequence of lemmas that we put together. Okay, now if we do this, we will be done with the full proof of the sensitivity conjecture. Okay, and maybe list, you know, the steps towards the end, but let's focus on what this, how to approach this. Okay, so this is one matrix B1. You know, even the original adjacency matrix satisfies this in this case, but not always. If I multiply it, what do I get? No, it became a parallelogram. Okay, and if you multiply it, it's not easy to check. It's not hard to check that this actually holds. You do get 1, 0, 0. You know, here I just, when I do the cross product, I get 0 and the same thing. Okay. Now let's do H2. We already saw one signed adjacency matrix, but actually I want to show you the more step-by-step version so that we identify a pattern. Okay, so this is the graph. The graph contains, the vertices are bit strings of length 2, and these are the edges. Okay. And what's the adjacency matrix? Okay. So it's a 4x4 matrix. Without even looking at what you have here, what pattern should you expect here for the adjacency matrix? These are all strings which begin with a 0. So what should you expect here? 0, 1, 1, 0, right? And that's exactly what you have there, right? So there is some self-similarity in these matrices. Okay, there's some sort of recursive nature, which is what makes everything easy. Okay. And let me just draw this sort of fictional line. And what about in this other diagonal block? Among all strings, we start with a 1. What matrix should we see here? We should again see the same thing, right? Because once I fix the first bit, in the remaining things, the graph is basically what you had before, right? So that's why induction is helpful. Okay. How about the off diagonal blocks here? How about 0, 0, and 1, 0? Will they be connected? Yes, because I'm changing 1, 0 to a 1, but not the other 0 is staying the same. Okay. And I would get 1 here and 0 here and 0 and the same thing here. Okay. So there is some pattern in this H2, right? When we think of it as this block diagonal matrix, I think of this as 4 blocks. So the top left block is just H1. Bottom right block is H1. And those two are identity matrices. Okay. So I can, instead of writing down the exact entries, I can compactly write it out as this. Okay. And this is the thing that we actually use to get the sign. Okay. So here we somehow got lucky that I had the simple enough thing so I could build the signing. But now to get here, I'm not going to start from scratch. So what's the first, maybe guess you would have for how to build B2? Let's say we already have B1. How can I get B2, the signing, such that B2 squared is 2 times identity? Any guesses? Take a guess and then we'll see and fix it. Somewhere you have to use B1. How can I bring that into play? Okay, so well, okay, so let's do B1 here. You said minus B1 here, right? That'll also work actually. Bottom right B1. Okay. Okay, that's the guess. And let's see if it works. So what is B2 squared if I follow this? I mean, we are multiplying block diagonal matrices, but we can do that. Right? We don't have to open up everything all the time. Okay, let me draw it a little bigger. Okay. So when I multiply block diagonals, I get, B1 squared plus I2. Right? So this block is like this. So it is B1 squared plus I2. Okay. And what about this? 0, which is kind of what we want, right? Because we wanted identity when you saw the square. This 0. This again is good. We get I2 plus B1 squared. Okay, but what is B1 squared? 2 times I2. Sorry, B1 squared was, 1 times identity. Okay, so I just get this equals as a matrix, I just got 2 times identity, which is what we really wanted. Okay, and that's what I wrote down here. I guess the opposite, like, I put B1 here and minus B1 here, but it's the same thing. Okay, make sense? Okay, so now you can imagine how we are going to do the general construct. Right? I'm not even going to do 3. It's a little bit painful to draw it. So for Hn, once again, there are 2 to the n strings, right? But I can put the strings such that in the first half, I have all strings which start with a 0. And the second half, I have all strings which start with a 1. Okay. So these are all 0 dash 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 0 dash 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 0 dash dash dash. And this is 1 dash 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 1 dash dash dash. Okay. So what will I see here? What matrix would I see here? What pattern would it be? Because I'm fixing the first 0, right? So the graph is kind of only determined by what's left. And that's just going to be Hn minus 1. Okay, so here I'll have Hn minus 1. And the same thing here. What about this block? What would it be? Identity. Okay, why is that? I'll say identity 2 to the n minus 1. Because here, what's happening is I have strings which start with a 1 and something. 1 and something, right? In some sense, this 0 and 1 are already different, right? So the only way the 2 strings will differ by exactly 1 bit is if the rest matches exactly. You already made one difference, so the rest should match exactly. Okay, we go to kind of the picture. What we're really saying is, maybe let me just draw that once. Right, so this is like 0, 0, 0. Okay, so this is H2 essentially with 0 padded in front. And this would be H2 with 1 padded in front. Okay, and across these, you would just connect the corresponding vertices, whatever is sitting there, right? Nothing else. Right, so the hypercube graph has this very nice inductive or self-referential structure, and that's what really helps. So what should Bn be now? So we'll make this Bn minus 1, and the other one to be, I guess we are doing, it doesn't matter which one you mix. Okay. This would work. And you can check that when you square it, you get exactly n times n. Right, so let's just do that. So Bn squared is going to be no. Okay, we can do the block diagonal matrix again. So here we get Bn minus 1 squared plus identity, which is n times identity now. 1 to the n minus 1, because this gives me n minus 1, I'm getting 1 extra identity, right? And this is 0. 0 n times identity. Okay. So just by this inductive construction, we do know now that there is a matrix which satisfies this constraint. Okay. All right. So let's just take a quick look back at everything that we did, right? So we started out with sensitivity that we wanted to show for every f. Right. And then we went to okay, so we had to show this. For any subgraph H of Hn, the max degree is at least square root n. And this implied this. Okay. And then to do this, we said Cauchy's interlacing theorem plus signed adjacency. There exists a matrix Bn. There exists a signed adjacency matrix. Okay. So this was known for a long time, but I think this, like, this was a big, big jump. Right? It gave us a new lever. Somehow just had to build this matrix, which gets this root n. And then we said, this is linear algebra. There exists a signed adjacency matrix. such that okay. And finally, this was just by induction. Okay. Question? You had a
No,
question? Okay. Any questions about this? It's a really remarkable proof. It's kind of a problem that was open for a long time, and then you had this somewhat non-elementary in that you're using this Cauchy interlacing theorem and so on, but given what all stuff people were trying for this before, it's very surprising, very pleasing to see a very clean solution. Okay. All right. So let's take a 5-minute break. And when we come back, I'll talk about, maybe example and how to prove this step. Okay, how do you go from this graph theoretic version to the actual sensitivity conjecture? That's also not too difficult. You just have to kind of work with it a little bit. Okay. And then maybe talk about the example. All right. Okay. Let's take a 5 minutes break. So maybe, I don't know if I'll definitely do the example. This step is interesting, but it's a little bit like, you need some Fourier analysis. So, but yeah, let's do the example. Okay, so for the tightness of the sensitivity conjecture, so I'm going to write down a function which has degree n, and the sensitivity is actually exactly root n. Okay. And what is this function? There are two ways to view it. I'll write down the formal equation in a second too, but imagine I write down this n variables in blocks of root n. Okay, so this is a root n by root n block matrix where I'm just grouping the entries x1 through xn in terms of blocks of root n. Okay. And the function I'm going to define is t of x is 1 if a row is all ones and 0 others. Okay. If there is a single row which is all ones, or if there is at least one row which is all ones, then the function evaluates to 1, otherwise it evaluates to 0. Okay. So, you can also think of it as just saying I have a giant R here, and then I have ants. Right? So either the first row is all ones, or the second row is all ones, or the third row is all ones, and so on. Okay. So you're grouping the variables into blocks of root n each, taking an AND of these blocks and putting an OR. Okay. Now it's the degree of this function is actually root n or is n. You can write it down explicitly. It's by basically taking the polynomial for OR and then the AND. Okay. Maybe let me just write like this is just. Okay, so you're taking the AND here, so multiply all of them. If any of those is 1, this whole thing becomes 0, so you get 1. And if everything is 0, then you get 0. Okay. If you expand it out, you have root n, root n, root n. So all of those things multiply and you get exactly n as the degree. Okay. So f equals this, f of x equals this. So degree of f is actually.
You want to remove the product.
And the sensitivity of f is, I claim, is root n. Why is that? So there are two cases. Either t of x is 1 or t of x is 0. Right? Either your function, or not t, f. Either your function evaluated to 1 or evaluated to 0. Okay. So if it evaluates to 1, what does it mean? At least one of these ANDs is a 1. Okay. And so then my claim is that the sensitivity is small. Why is that? So how bad can the sensitivity be? If the function evaluated to 1, then one of these ANDs must be 1s. I'm saying that implies that the sensitivity is small. Why? Yeah. You have to change one of these ones, right? Otherwise, the function is not going to change. So that means that the only coordinates that can actually change the function must be inside it. Okay. So this is at most root n, right? On the other hand, if it is 0, my claim is the sensitivity is once again small. Why is that? The function is 0, meaning to change it back to 1, you need to change something, but how can you change? Any guesses? Yeah. Yeah, you can change at most root n, right? Because every row will have a 0. And because the function evaluated to 0 means that every one of these ANDs was 0. So every row here had a 0. And if you don't flip that, you're not going to change. So you have to flip one of them at least. Okay. So those are the only things that can cause. So it is root. Okay. All right. So this is an example which actually shows that the sensitivity conjecture is done. And people knew this example before the proof was known. Right? And you can use this also to build the graph example exactly. Okay. All right. So in the interest of time, I'll skip the proof of this because we're a little bit behind in what I wanted to do, but that's okay. Okay. So that's what I wanted to say about sensitivity conjecture. I mean, as I said, there's a lot of applications, interest that led to this problem. But for us, one of the key takeaways should be the power of spectral graph theory, right? Seemed like a very combinatorial or graph theoretic question. And then once you bring in Cauchy's interlacing theorem, and also this very nice insight that you look at signed adjacency matrix, you get it. Okay, there's a question. Think you need to remove the product symbol from the formula for f of x. Let's see. Yes, that is true. Good catch. This should not be there. Okay. Right. But once we had this, okay, let's look at the Cauchy sign adjacency matrix. And then once Cauchy interlacing theorem came in, it became much, much nicer. I just needed to find a single signing which satisfied this. And remarkably, we hit the exact delicate balance that we, right? We needed root n, we got exactly 2 to the n minus 1, which are root n, 2 to the n minus 1, which are minus root n. Okay. All right. So this is the second topic, and I think that's all we are going to see about spectral graph theory, unless depending on how we go towards the end of the class. Okay. So maybe one take care of the first two topics should be that, okay, we just saw two brilliant applications of spectral graph theory, and there are tons and tons of applications. Okay. So the next topic that we are going to study is called is about what is called the sunflower conjecture. Okay. This is a problem which has its origins in pure combinatorics. Okay. But it has found tons of applications in computer science. And then eventually this most significant progress for that came from methods from computer science. Okay. So once again, there's so much history and this has been opened. I mean, this was coined long ago by Erdős and Rado in 60s or something. Okay, so there's a lot of history on this problem, tons of applications. We're not going to touch many of them. I'll just state the problem and then maybe a little bit of applications to CS. Okay. And then we'll see the proof of that over a few lectures. And the proof is very computer science. We're going to do some compression, do some counting, some methods which have their origins in like information theory and so on. Even though we don't use those things explicitly, we're going to do some accounting. Okay. All right. So what is the sunflower conjecture? It's basically trying to identify patterns in sets when I just tell you that you have many sets. Okay. So the objects of study here are what are called set families. So let's say I just give you a collection of sets. Okay. A set family is basically a set of sets, right? Each set is from some universe, 1 through U. Okay, we'll change the notation later on, but for now, just imagine I have a universe and then I'm taking sets one after the other. All right. And I'm not going to say anything about how we are picking these sets, except that each set is small. Okay. What do I mean by small or fixed? We're going to think of K as being small and the size of the universe as being something out of our control. Right? So maybe universe size is 1 billion, but I'm just telling you, okay, you're picking sets where each set only has 10 elements. Oh, wait, did I start recording again? Okay, I did. Good. Okay. All right. So fixed just means that that's our main parameter. Okay, don't think of it as like a constant, but something that we control, or that's what we are parametering the family over. The universe is kind of unbounded. Okay. And typically this is something that happens in combinatorics and also in computer science, where you try and show that if I pick many items, then you see some pattern just because you're taking many things, right? And in sets, there are different patterns we can shoot for. What kind of patterns would you be interested in? You might think of disjoint sets. Okay, maybe I have sets which are no intersection or anything like that. Okay. In fact, the pattern that we are looking for is kind of what you see in the Venn diagram. Right? Okay. And this is again a beautiful definition, somehow. It's a seemingly simple definition, but it has found many applications. Okay. So a sunflower is basically a collection of sets where if I draw the Venn diagram of the sets, it looks like a sunflower. Right? So, I can imagine, let's say I'm just drawing some Venn diagram, right? So I can have this, maybe this is the other set. Things like this. I can see the Venn diagram could have all kinds of things like this, right? This is S1, S2, S3, S4. The intersection patterns could be all over the place. Sunflower is looking for a very regular pattern in this Venn diagram. Okay. In particular, I want an intersection pattern which looks like this. Let's see how well I can draw. Okay. And so on. Okay. It's a Picasso sunflower. So what does it mean? So in some sense, the Venn diagrams, they have a very regular, and all of the sets have a very nice intersection pattern. Any two sets intersect in a common core. Okay, so let me really draw maybe a combinatorial picture. So think of this as a core, right? And then every set is like this. It has the core and then something else. Okay, so these are called the petals, right? So a collection of sets S1 through SR form a sunflower if okay, for any two sets, they only intersect in one core. Okay, so all of these pairwise intersections are exactly the same set. Okay, so there is some common element where any two intersect, but if you take that out, they become disjoint. So S1 intersection S2 is the same as S10 intersection S11 and so on. So it's a pretty rigid structure. You're saying you have a collection of sets But any two, the intersection pattern is exactly the same. Which also means that all of them actually contain this core. And then once you take out the core, they're all disjoint. There are various ways of thinking about it. Okay. All right. So now the question that it's really, there are lots of questions you can ask in Ramsey theory and combinatorics and so on. Basically, you identify some pattern and then you say, what if I just give you lots of elements? How many elements do you need to see before you know that you will find this pattern? Okay. They're saying, I give you lots of numbers one after the other. How many numbers do you need to see? So before you see some pattern. Okay, in this case, they were asking question, how big must the family F be to contain sunflower with So like, let's say, R is 3, 2 is trivial, there's no condition. Even a sunflower size 3 is not trivial. I tell you, okay, K is fixed. You start picking sets one after the other. How many sets do I need to see before I'm guaranteed to find a sunflower in the sets that you picked? Another equivalent way to think about it is give me as many sets as possible which do not contain a sunflower. Just, same thing, okay? Usually we think of the positive thing because it's just easier to prove that. All right. And this is where, we think of K as a parameter matters in that we're not going to put any bound on the universe, right? So universe can be anything. As long as I'm picking sets of size 10, you want to say, if you pick more than, let's say, 1,000 sets, you are going to see a sunflower of certain size and so on. Okay, that's the kind of statement we're shooting for. And the first such statement was actually shown by Erdős and Radov themselves. I think it's K factorial. If size of F is more than something, then F contains, oh, actually, let me write it properly. Okay, so this is set up. I have a bunch of sets where each set has at most K elements from some universe. Then if N is more than this, F contains a sunflower with sets. Okay, that's the claim. We'll figure out what this is. I don't want to write the answer, or I don't remember it, but I know the proof, so we'll see it. Okay, it's not important to remember it. Okay, let's try and figure out, in some sense, it's like the first sort of maybe greedy approach, and then we'll see. Okay. So one thing to keep in mind is, let's say I find R sets which are all disjoint. Is that a sunflower? Kind of, in the definition, but it is actually a sunflower because it just means that the core is empty, but the main thing is the intersection pattern is always the same. So that's what we're really shooting for. Okay. The intersection patterns are exactly the same. Okay. Because, all of them have empty intersection. So they satisfy this constraint. So disjoint sets are a sunflower. Okay. So if, our sets are disjoint, we are done. Okay. So what does this mean? So let's say I start greedily and I pick one set S1. I pick another set which is disjoint from S2 if it exists. Okay. Another set S3. If it's disjoint, I'm happy. I'm just going to start with this. Okay. At some point I get stuck. So this is a maximal disjoint collection. Okay. I start with one set S1, whatever that is, and then pick any set which is disjoint from S1 if it exists. Pick any set which is disjoint from both of them. Okay, if it exists, and at some point you stop. Okay, so these are all maximal pairwise disjoint collection. Okay, if L is greater than or equal to R, we are done. We found a sunflower with R sets. Okay. What if we did not find such a, we got stuck, maybe we only found 3 disjoint sets and we got stuck. Whereas R we were shooting for was something higher. Okay. So we're trying to find what bound here which guarantees that I can find R things here and K, where each set is K. So these K and R are the parameters. We want something independent of U and as small a bound here as possible. Okay. So far what do we have? The Venn diagram looks like this. I have S1, maybe S2, S3, up to SL. L is less than or equal to R minus 1. That's what we know. Okay. And each of these has less than or equal to K elements. Okay. What can you tell me about the other sets in the collection? My claim is now you know something very strong about the other sets in the collection. What do we know about them? They will intersect at least one of them, right? Because we could not find anything else which was disjoint from everything, right? So that means that for every S, which is okay. So let I be all of the elements in these disjoint sets. Okay, so I have at most K here, K, 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 but the total number is at most R minus 1. Okay, so in particular, this means that every set which is not this must intersect I. Okay, because it must have some overlap. Otherwise, I could find a disjoint set, I can add it to my collection, grow it. So every other set must overlap somewhere. Maybe either here or maybe it could intersect 2 things. It doesn't matter. It must intersect at least one of them. So in particular, it must intersect the union. Okay. And so what's the size of this I? The number of elements here is at most. I have R minus 1 sets, each of size K. So it's at most K times R minus 1. Okay. All right. Now, let's think of this number as, whatever n of K comma R. That's what we're trying to bound. Okay. All right. So we are basically almost done now, right? So what we know is that every set S in F must intersect I. This is a very strong constraint. Every set must intersect this union. Everything which is not one of these things must intersect it because we couldn't grow anymore. And those things are actually in here. So every set must intersect this. Okay. And we can now look at which element here they intersect. Okay. So what do I mean? So let's say this set I is I1, I2 up to some I, M. Here's some elements. Maybe it's number 17, maybe number 19, whatever you have. Okay. So there exists an element I in I such that let's say I look at all sets in F that contain the element I. Okay. Your set has every set intersects one of them. I'm saying look at all things which contain element I1. All sets which contain element I2. All sets which contain element I3, so on. Okay. So what can you say about how big this can be? Okay, maybe let me write it a little differently. This is the definition. And now claim is that there exists I in I such that okay. So every set must intersect one of these I's. So one of the elements must actually contribute for many of the intersections. There are only M elements. So at least one of these elements actually is responsible for about average many intersections. Right? So every set must hit one of those things. And there are capital F many things. So on average, one of them should have capital F over M intersection. Okay. And this is where we gain something, right? And there's this notion of a link I can define. So I'll write it like this is S/I, where okay. So I take all sets which contain the element I and take out I. Okay. What can I say about this size? Is at least the size of F divided by K times R minus 1. Okay. How big are the sets in this family? K minus 1. So now I can use induction. Okay. So if size of fi is greater than or equal to n of k minus 1 comma r, we can find a sunflower of size. Okay. And when I take out an element and I find a sunflower, if I put it back, I will still get a sunflower. Right? That just goes into the core. It's part of every set. Okay. So this gives us the recursion n of k comma r is at least k times r minus 1 times n of k minus 1. Okay. So, you can solve this and eventually you just get r minus 1 to the k times k factorial. Okay. So that's why I said, it's not important to fill this out earlier. It's not the formula, it's really the recursion or the inductive thing that helps. So we just said, maybe sets of size 1, I can find a sunflower. Sets of size 2, then I do this sort of greedy thing, find a maximally disjoint thing, and then I can reduce the size by going to this. Okay. Any questions? Yeah. Are we throwing out the SS? No, we're keeping them. Throwing them wouldn't hurt us, but we can keep them too. Okay, it just makes the induction clearer because the condition that every set intersects the union still holds. Right, so that's the only thing that we cared about, right? Here, this is what we really cared about. Okay. All right. So this was shown in the 60s that this bound r minus 1 to the k times k factorial. In the same paper, they conjectured that k factorial is unnecessary. That you shouldn't have a k factorial, it should only be like an exponential k. And this problem was open for a long time. And then a few years ago, there was progress on it. And that's what we're going to talk about. Okay. So I'll see you all on Wednesday. Maybe I'll just do this proof a little bit slowly again, because the final proof also builds on this. Okay. All right.